So here is just a quick summary of all of the different types of things to look at when you're looking at limits here. So I kind of separated them by what that number x is approaching, like what significance that has to the graph. So you can think about the graph, visualize what's happening at the graph. You don't necessarily have to draw the full graph, but you have to kind of think about what's actually happening. So I'm going to start with the removable discontinuities. So when I'm looking at this first one here, as x is approaching -4 from the right. So we know that -4 is a removable discontinuity because the x plus 4 is going to cancel in that numerator and denominator there. So really what's happening at this here, I'm going to show you a picture of what the graph looks like here. All right, so this is the graph of it. What's happening right here at -4, if it lets me trace it along here, is right here at -4, you can see it's that open circle. It says it's undefined right there because it still makes that denominator 0. But really what happens is the rest of the graph kind of continues as normal. You can see I actually graphed the function without that x plus 4 in there. If you graph that function, it is actually just exactly the same function right here. And this one, -4, is defined right here. It's 2 1/3 on that one. So again, you can see that there is a point there, but on this one, our function, that point is just missing. But when you're thinking about the limits of it, so here again, it was, hold on, let's see if it lets me write on it here. Again, it had a missing point in the graph, but as I'm approaching it from the right and as I'm approaching it from the left, it's really approaching whatever that y value basically should be in the graph. So to find it, to find the limit on this, all we have to do is find what the ordered pair would be for my removable discontinuity. So if I put -4 in, I get -7 over -3, which is +7/3. My limit is going to be 7/3 there. So that was from the right. I showed from the left as well. Again, it's still going to approach that same exact y value right there, which means this limit is also 7/3. So again, because the limit from the right and the limit from the left are exactly the same, that means the limit as x just approaches -4 does exist. It's 7/3. So I did another one here. You can see that x equals 0 would be a removable discontinuity because that factor can cancel. So we really just want to know what is the y value when the x coordinate is 3. So I can substitute it in. That means in my numerator, I get 3 times -1. In that denominator, I get -5, which means I get -3 over -5 or +3/5, and that's the limit. So the removable discontinuity, if that's what x is approaching for our limit, it's really just what is the y coordinate, because from the left and from the right, it's going to be approaching that missing y coordinate. So vertical asymptotes, let me move it up here. Vertical asymptotes, again, still make that denominator equal to 0 here. So give me a second. I'm getting used to making a video again here. So if I'm looking as x is approaching 2 from the right, we know that that's a vertical asymptote at x equals 2 because that makes the denominator 0 and that numerator, there is no factor that matches it in the numerator there. So we really have to think, if it's an asymptote, basically I have a couple options here. So I'm going to have from the left, it go to +infinity, and from the right, it goes down to -infinity. Or it could be from the left going down to -infinity and from the right going up to +infinity. If it's a single asymptote or a single, single factor, so it's x minus 2 not squared, that's always going to be the case. So they're going to be going in opposite directions. So we need to decide, is it going to be going to, on the right, is it going to be going down to -infinity or is it going to be going up to +infinity? So to do this, we can kind of think, we can choose an x value that's maybe just a little bit to the right of +2, because that's 2 from the right. I usually just think about like 2.1 would be just a little bit to the right of it, because that's going to be nice and close to that asymptote there. We don't actually need to do any full calculations. We just want to decide, would my value be positive or negative here? So if I put 2.1 into this x minus 3 factor, it would be negative. If I put 2.1 into the x plus 1 factor, that factor would be positive. If I put 2.1 into the denominator, x minus 2 factor, that factor would be positive. And then 2.1 plus 4 would also be positive. So my numerator would be a negative. My denominator would be positive. That tells me a negative divided by a positive, that would be negative infinity. If I went, I'm going to look at the next one here. If I did from x, or x approaches 2 from the left, again, choose maybe a number a little bit to the left of 2, maybe about 1.9. Again, you don't actually have to calculate it. We're just thinking positive, negative. So 1.9 minus 3 would be negative. 1.9 plus 1 would be positive. 1.9 minus 2 would be negative, and 1.9 plus 4 would be positive. Notice the difference between that one and the one we just did. The only part that was different was that factor x minus 2. Because if I'm a little bit to the right of it, that factor is going to be positive. If I'm a little bit to the left, that factor is going to be negative. So now I have a negative divided by a negative. This is going to be positive from the left. So that tells me, just to draw a quick picture of it, from the left, it's going to positive infinity. From the right, it's going to negative infinity. Because they're going in different directions, the limit as x approaches 2 does not exist. So for the next one, the limit as x approaches negative 1. Again, this one has a removable discontinuity. You can cancel that factor out. But again, that's still a vertical asymptote. For this one, because again, that's just an x plus 1 to the first, you know from the right and from the left that x plus 1 is going to be opposite factors of each other. We know automatically, without even really having to do any work, that this limit is not going to exist because from the left and from the right, they're going to be going opposite directions. Now, the next one I did, what if I asked you negative 1 from the right? What if we did want to calculate that? So again, we could choose a number just a little bit to the right of negative 1. So maybe negative 0.9, something just a little bit bigger than that. So the numerator, negative 0.9 minus 3 would be negative. Negative 0.9 plus 1 would be positive. A negative divided by a positive would be a negative. So from the right, this time it's going down to negative infinity. Now, the next one here, sorry, I have to go back to the mouse to move it back up. For the next one here, notice the denominator is an x plus 1 squared right there. Okay, if it's an x plus 1 squared when I'm looking at this, that's going to change things. So if it's an x plus 1 squared, I'm just going to draw it over here. It's either going to both be going up to positive infinity or both be going down to negative infinity. Because if I think about it here, if x is approaching negative 1, if we chose a number a little bit to the right or a little bit to the left, we're actually going to get the same thing. So say I chose negative 0.9 again. This first factor would be negative. This factor would be positive. My denominator is going to be positive because it's any number squared is always going to be positive. If I chose a number a little bit smaller than negative 1, x minus 3 would still be negative, x plus 4 would still be positive, and notice my denominator, because I'm squaring it, would actually still be positive, so it's going to be the same in both sides of it. So I have a negative divided by a positive, which would be a negative infinity. So that tells me that this graph, they are both going down to negative infinity. So if I look at this one, x approaches 4, same idea. Again, if I think to the left or to the right, it doesn't even really matter. They're both going to be the same. So if I did like 4.1, x plus 5 would be positive, x plus 2 would be positive. That denominator is going to be positive. If I did 3.9, they'd all be exactly the same. So from the right and from the left, it's going to be the same. It's going to be going up to positive infinity. Last one here, I just said from 2 to the right, just to show that it's the same thing if I asked you from the left or from the right. Again, that numerator would be positive. The denominator, because it's squared, is always positive. That one would be a positive infinity there. Okay, if I look at something that's just a defined point on this here. Let me get rid of this here really quick. Again, we know it's just a regular point on the graph because it doesn't make the denominator 0. So 1 does not make the denominator 0. anything that makes the denominator 0 would be an undefined point. So it's just a regular point on the graph. So I don't know even where it is, but it would just be a point on the graph. So from the left and from the right here, it would both be approaching just whatever that y value is. So if I just wanted to know what the y value is, I could plug it into the x plus 4, but I don't need to since that cancels. I would do 1 minus 3, and I would do 1 plus 1, so that would be negative 1. That's going to be the y value that we have. Same idea if I asked 3 from the right. Again, it does not make your denominator 0 at all. So that means it's just going to be a defined point on the graph here. So you'll notice that 3 actually does make the numerator 0, which just tells us it's an x-intercept. So we would have 0 times 1 or 0 times 4 over whatever. It doesn't even matter that y coordinate's going to be 0. That just tells us it's actually an x-intercept, which doesn't really mean anything with limits, but it can kind of give you an idea of what you're looking for with the graph. So defined points and removable discontinuities are actually kind of the same. We're just finding what's the y value, because from the left and from the right, it would be approaching that same y value. All right, last thing to look at would be our horizontal asymptotes and slant asymptotes. This is always as x is either going to positive infinity and negative infinity there, because what's happening at positive infinity and negative infinity is that's our end behavior. So that's determined by your horizontal asymptotes and slant asymptotes. So what we have to decide is which does this have? So when I'm looking at this first one, I have it still in factored form. I didn't mention that. Usually a lot of times they're not in factored form and we would have to factor it. Just for simplicity of this video, I made them all and most of them in factored form. But if I were to multiply it out, we'd have x squared plus whatever. The denominator would be x squared plus whatever. Again, I could actually multiply that out, but I'm not going to. Because really what matters here is that the degree of the numerator is the same as the degree of the denominator. So as x is getting really, really, really big, essentially those are going to be so close to each other that when you divide them, it's going to get closer and closer to the horizontal asymptote of y equals 1. That means the limit as x approaches infinity is 1. If I change that to the limit as x approaches negative infinity, that limit would also be 1 because at the ends, it's going to approach that horizontal asymptote. For the next one here, again, same idea. X approaches negative infinity. I just have to think, if I multiplied this out, I'd have a 6x squared, okay, minus 3x, and then this denominator would be an x squared, etc. So again, as x is approaching positive or negative infinity, as those numbers are getting either really, really big to like, a million or negative a million, really, really small like that, the numerator and denominator are going to be very, very close to each other, except the numerator is going to be 6 times all of that. So that means my horizontal asymptote is actually y equals 6 right here, which means the limit as x approaches negative infinity or positive infinity would approach that horizontal asymptote of 6. This next one, the degree of the denominator would be an x squared, which means if that denominator is going to get way bigger than the numerator because I'm squaring a big number, our horizontal asymptote would be y equals 0. So the limit as x approaches either positive or negative infinity is going to be 0. Now these next three all have slant asymptotes. You don't even need to fully calculate the slant asymptote to think about the limit. All we need to think about is, would it have a positive slope or would it have a negative slope? So if I'm looking at this first one, if I divide these, again, you don't actually need to fully divide them all, but if I divide them, really, when you do long division or synthetic division, the first term when you divide is always going to be those first terms divided by each other. So that means your slant asymptote is going to be 1x plus or minus something. Doesn't even matter what it's going to be. But that tells us that the slant asymptote would be going in this positive increasing direction here. So if I want the limit as x is approaching negative infinity, that means it's going to follow the direction of that slant asymptote, like it's going to go follow it down. It doesn't even matter which side of the asymptote it's on, it's going to keep going down with that slant asymptote. So that limit is negative infinity. If I'm looking at this next one, same slant asymptote, right? It's the same problem right here. It'd be x plus whatever. But here I'm going to the right as x is approaching positive infinity. Again, this would be getting closer and closer to the asymptote from either direction, but it's going to be increasing without bound. That's going to go to positive infinity. Last one here, if I divided these, again, it has a slant asymptote, we would divide these and we'd get y equals negative 3x, again, plus or minus something, a y-intercept there. But that tells us that our slant asymptote is going to be decreasing. So as x is approaching infinity, it's going to follow the path of that slant asymptote, and this one would be going down to negative infinity. Hopefully that summary kind of helped explain them a little bit. Let me know if there's any other questions here.